Let's move now to process scheduling. We have a dedicated lecture about scheduling, so this is just a simple introduction here. So we said that the context switch needs to be fast. This implies that when we need to decide what is the next process that should run, we should be efficient. Now, how efficient the operating system is depends on the data structures that it uses to maintain the information about the processes or the process control blocks. Here you have a first example of the trade-offs I mentioned between space and time complexity. You can keep everything in a single data structure, okay, that is potentially simple. It reduces space complexity, but then it's not optimal for time complexity. If you keep everything inside the same data structure, you might need to traverse the entire data structure to find out what is the next, which is the next program that you want to run. So the operating system does something smarter than this. It actually keeps different queues, okay, in which it stores the process control blocks. One queue is the queue of processes that are ready, or processes control block that refer to processes that are ready. And then there are different queues depending on the input-output device, okay? So you can have a queue that is containing only the process control blocks of processes that are waiting for the disk. And to say that one process changes its state from waiting to ready could actually mean that the process control block of that process is removed from the queue that refers to a disk unit, and it's added back to the queue of the ready processes. This organization helps in reducing the context switch time, because if you want to know what is the next ready process to run, you don't need to check among all the process control blocks you have, but you can just pick the next in the queue of the process control blocks that are about ready processes. So this is the, let's say, life cycle of the process. Once it starts, it gets into the ready queue and it gets some CPU time at a certain point. It might just terminate, or some other things could happen. There can be a request, okay? And then it will go in the queue of some input-output device until it actually gets, or until the input-output is done. It might be that it's the time slice that is given expires, okay? The operating system might say, okay, well, each program runs for 10 milliseconds. There is always this clock ticking and creating interrupts, let's say every second. So sometimes the operating system might wake up and check how much time it has let a certain process run and then put it back to the ready queue. We will see that processes can fork a child, or let's better said, they can create other processes, and this could be a reason why you stop running this process and you start running a different one, okay? Or they could be just waiting for an interrupt, okay, in which they will stay in this waiting state until they get an interrupt, and then they will go back to the ready queue. Now you have both short-term schedulers and long-term schedulers. As the name suggests, the short-term scheduler selects the process that should be executed next, so the process that should get the CPU, okay? And this is maybe the only scheduler you have, or for sure the scheduler you need, because it's the one taking decision immediately about what to run next, okay? You can also have long-term schedulers, okay? So it might be that there are processes that need to be put to sleep because there are not enough resources. We will see this thing in a certain number of lectures when we talk about virtual memory, okay? So these are, let's say, taking decision on a larger time frame than the short-term schedulers.